Hello and welcome to this Isabelle Hute USA webinar. My name is Matthew and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading presentation in the upper left is the primary window for today. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now let me introduce today's presenter. With us today, we have Dr. Jan Marien, the Executive Vice President for Research and Development from Isabelle Hute Huesler. To read more about Dr. Marien, please look at the speaker bio window right next to the main presentation window. And Dr. Marien, welcome to today's event. And with that, I will pass things along to you to get started.
Thank you very much for the very kind introduction. And I have to say I'm really impressed about the number of participants here in this webinar. So it seems to be a topic of really hot interest. And I want to talk now about new approaches to obtain higher accuracy, higher power density, and more robustness for a very well-known passive electronic component, the shunt resistor. We are convinced that electricity will be the major form of energy to decarbonize our world. This is driven mainly due to the very high efficiency you can obtain with electricity driving all the different applications. And thus you will find this in all the different sectors. In mobility and transportation, you're well aware of electrical cars, driven as well by batteries or by fuel cells. This will be also true in industrial automation. This will be also true in heating or cooling systems for buildings. And obviously, this will be also the case for the energy system itself. As a consequence, we will see a substitution of fossil fuels by electricity. And thus, we will see an enormous increase of power generation generated by renewable energy sources. The amount of electricity needed will be increasing, but at the same time, the amount of primary energy is reduced. And finally, what we also will see is that all the energy flows within the energy system, but also between the different sectors, will be accompanied by information flow to make all this an intelligent or a smart system. Due to the high efficiency of electricity, the modern world will be driven by power electronics. Power electronic systems are built around semiconductor devices which transform one form of electricity into another form of electricity. For example, in solar power plant installations, the DC current of the solar cell is converted into an AC current used for the power grid. In home appliances such as cooling systems or heating systems, these power electronics are used. They are also found in industry automation such as robots, such as drive systems used in industry automation. But you also find them in electric cars, both battery-driven as well as fuel cell-driven electric cars. New semiconductor devices such as wide bandgap silicon carbide or gallium nitride devices enable even more power density in these circuits. For all passive components used in these applications, it means we have to deal with higher temperatures, with more accuracy, and with more long-term stability. And we have to design our passive components to become as robust as possible. As I mentioned in the introduction, shunt resistors are used for current measurement in a lot of applications, and these need to fulfill all the above-mentioned requirements. The basic principles of shunt-based current measurement goes back to the year 1821, when Georg Simon Ohm observed during his experiments with electrochemical cells the most fundamental law of electrical engineering, Ohm's law. I think you're all well aware of that. If you want to build a real physical resistor, you typically use metal alloys to do so. These metal alloys have to fulfill 4 basic requirements to build a good resistor. The first requirement is that the material should exhibit a high specific resistance. This is important because you have to be able to generate a significantly high voltage drop out of a limited volume and a limited space used to form the resistor. Secondly, the material should show a low temperature coefficient. This is important because you want to have your measurement as independent as possible from the temperature itself. Thirdly, the material should have a low thermal EMF to copper because temperature differences at both ends of the resistor should not contribute to any mismeasurement of the current. And finally, you need a long time stability so that the resistance value remains the same all over the lifetime of the resistor. In this image, you see a typical resistor which is used in high power applications. It consists mainly out of 3 parts. To the left and to the right of the device, you have the copper connector, which is used to connect the resistor with the bus bars and to feed in and feed out the current. In the center of the device, you find the resistance material itself, which forms the resistive element. We have a couple of different materials available, which, by the way, are all manufactured at our own metal shop. They differ primarily on their resistivity and thus allow us to manufacture a wide variety of resistance values with nearly the exact same geometry. The joining technology used to join the 2 copper stripes with the resistance material in the center is electron beam welding. This is a highly stable production process. It's cost efficient, it's very accurate, and it has an extremely thin welding area, which is only about 1/3 of the material's thicknesses. And this process has a low influence of the overall resistance. From a customer point of view, one very important parameter is the total tolerance over lifetime. The total tolerance has 3 main contributors. The first contributor is the initial tolerance of the resistor. The second contributor is the temperature coefficient of the resistor. And the third contributor are the tolerances which are induced by the environmental influences during lifetime to the resistor. Let's first talk about the initial tolerance of the device. Due to the manufacturing processes, you typically have a distribution of resistance values of plus to minus 5% after manufacturing. If this is not sufficient, you can use trimming processes, which are well known for a couple of devices like thin film devices or metal devices, to reduce the distribution of the initial value. Typically, you can obtain a distribution of plus or minus 0.5% after a trimming process. The second contribution to deal with is the temperature coefficient of resistance. This is mainly driven by the temperature coefficient of the resistance material itself. I've put together some data here from our resistance materials we use actually to build our resistors. If you look, for example, to the green, to the yellow, or to the red line, you will find the relative change in resistance over the temperature range from minus 40 to plus 140 degrees C. In comparison, you will find in the same graph, at the same scale, in blue colors and in purple colors, the values for copper-based material or for pure copper. You can see these materials have a temperature coefficient which is factor 100 or a factor 1000 higher than this of the resistance materials. This is important to understand when we come to the device level. But let's have a detailed view on the temperature behavior of a resistor. It's important to understand that the TCR is not a linear function of temperature. I show two graphs here, one for the manganese built resistors and the other one for resistors built out of zeranine. You can find three graphs in each plot, one for 0 ppm, one for 50 ppm, and one for minus 50 ppm for the manganese resistors, and a TCR of 0, minus 20, or plus 20 for the zeranine resistors. If you take no further measures, then this represents a typical specification of a resistor with, let's say, plus minus 50 ppm for the manganese or plus minus 20 for the zeranine resistor. But obviously, you want to target for the green curve, the 0 ppm curve. How to do so? So obviously, the first thing you do is choosing the right alloy. And in our case, as we manufacture the alloy by ourselves, we have the opportunity to really fine-tune the material to the very best point to come as close as possible to the 0 ppm property. But then you also have to take care about an optimized shunt geometry. And I will explain this on the next slide. And finally, you can also use software to compensate for any remaining TCR of the resistor. So let's now talk on the influence of the shunt design itself to the TCR. Just as a reminder, we use a resistance material which in case of Isabellenhütte is very close to 0 ppm, and a copper material for the left and the right connection part which has a TCR of about 3000 ppm. Now if you look onto the left drawing, then you see typically you measure the voltage drop somewhat outside of the resistance material. So the TCR you actually measure is a combination of the TCR of the resistance material and of the amount of copper you have in between the measurement points and the resistance material. So even if you have a perfect resistance material, you typically find a TCR at device level because of that copper you have within your measurement path. Now let's have a look onto the drawing in the center of the slide. Here you see we have added two notches at the bottom of the device, left and right to the resistance material. And we also moved the measurement points where we measure the voltage drop into the region which is formed between the resistance material and these notches. In the region enclosed by these two notches, there's practically no current flowing. It's so-called shadowing of the current flow. And as a consequence, electrically speaking, the potential of these areas is exactly the same as this exactly of the left and the right border of the resistance material. Thus, if we place our measurement points into these shadowed areas, we have the high TCR of the copper eliminated from the measurement path, and we just measure the pure TCR of the resistance material. And this enables us to make a device which has really the 0 ppm TCR of our optimized resistance material. But there's also another approach possible, the compensation via software. What does this mean? We can measure our shunt at two temperatures at the end of line, and as we know the curve of the TCR, we can give the coefficients of a polynomial and write this on a label onto the shunt. Thus, our customer can read from this label, as well as the very precise initial value, as also the TCR of that individual resistor, and compensate by software in the application for the TCR. This enables the customer also to have a very precise current measurement in terms of TCR compensation. Finally, we have to talk about the environmental influences on the R value tolerance of the resistor. In this table, you see a number of environmental testings which are defined in the AACQ 200, which are performed for every qualification of a resistor or a resistor family. As you can see, there are several factors which may contribute to the tolerance over lifetime. And it's not a simple addition of all these factors, but it's a statistical calculations which are performed to estimate a realistic drift. However, we can state that high temperature is the main contributor to the lifetime drift of the shunt. With modern finite element simulation programs, we are able to very precisely simulate the electrical and thermal behavior of a shunt. Here you see the temperature profile of a BAS type shunt, which is operated at 1000 amps for 5 seconds. I have to note that currents above 1000 amp can occur during phases of great accelerations in BEVs, and these type of usage profiles are common in shunts which are actually designed for battery electric vehicles. So whenever we start with the development of a customer-specific shunt, we typically start with this type of simulations to properly design the shunt that the temperature rise in the resistance material of the shunt is not too high in terms for long-term stability as given by the usage profiles of the customers. The user load profiles may vary from customer to customer, both for the continuous current operation as well as for short-time current pulses. The heat capacity of the shunt material and the entire shunt, as well as low thermal resistance, are key to long-term stability because a well-designed shunt avoids overheating during operation. So in this slide we have put together the procedure we undergo during the development of a customer-specific shunt. First, we get the customer emission profile, which defines the temperature and the percentage each temperature is used during the application, and the total time of usage. We then take the qualification results of the ASCQ 200 environmental testing definitions, and with a statistical model we then can estimate the lifetime drift of that shunt. So far we have built now a huge database of different shunt designs, of simulations, of test results, and of the final estimation of the lifetime drift, so that we have a really good statistical evidence now to estimate the lifetime drift even during the development phase of a shunt. I would like now to mention another feature which is available by shunt design itself. It is measurement redundancy. As you can see in the upper left sketch, we have formed a pit in the center of the shunt by introducing a U-shaped recess. So we are considering now the measurement points 1, 2, and 3. In the image below, you see the result of an electrical simulation of this part. In color, you see the electrical potential, so red in the left, blue at the right, and then in the resistance material, the transition from red to blue, indicating the potential. And you also see the vectors of current flow within the sketch. And as you can clearly see in the pit, which is labeled 2, you have an electrical potential which is in the intermediate level between blue and red, which means that at this pit we can measure a voltage drop which is half or nearly half the voltage drop you have to measure when you measure over the entire resistance material. So for example, when you measure from point 1 to point 3. Or more formally speaking, the entire voltage drop, which you measure between 1 and 3 splits into a voltage drop between 2 and 3 and a voltage drop between 1 and 2. And this is a mathematical calculation which is always valid. This means that you can always verify your measurement by verifying the equation that the voltage 1 to 3 equals the sum of the voltage 1, 2 and 1, 3. And thus, this is a shunt design which enables you to have a redundant measurement and a self-diagnosable measurement within one shunt device. A lot of current sensing applications require a sensor design which fulfills the requirements of functional safety. In automotive applications, for example, this requires a design which is according to an ASIL level. And for higher ASIL levels, often a redundant measurement is required. Thus, for such an application, this shunt design is very favorable as you can implement a redundant measurement with one sensing device. So finally, we can combine this idea of redundancy with the idea of TCR compensation by design, and this is explained in this drawing. So again, you find two notches now at the top of the device, which are labeled T1 and T2, and we define two pairs of measurement points. One is the black pair and one is the white pair. Both pairs are compensated for TCR, and both pairs should measure the same values of voltage drop. So within one device, we are able to have a redundant measurement as well as a TCR compensated measurement. As mentioned in the introduction, also power density and thus current density is a requirement for new applications. And I will finalize this presentation by showing you some examples of products which show how we cope with this new requirement. In this comparison chart, you see well-introduced product lines in metal strip technology as well as in metal foil technology. And in the red circles, you see new products which complement these product lines for the resistance value of 0.5 milliohms to 6 milliohms. The WAX series is a 1206 and a 1213 component, which is available in 0.5 and 1 milliohm, and which is made out of full material. In contrast to the BVX series, which has a copper connection left and right to the resistance material, for the WAX series, the copper connection extends to the bottom, thus to the PCB side of the component. This is a very robust product design, which can operate very reliable at high temperatures, but also increases the current density by a factor of 3 to 4. As you see here, even for the small footprint of a 1206 or 1213 component, it can, dependent on the resistance value, have a rated power of up to 7 watts. The FMX series, which complements the metal foil product families, is available in 1206, 2010 and 2512 footprint, and the power rating is in the range of 1 to 4 depending on the size and the resistance value, which is again a factor of 3 to 4 as compared for the foil resistors. This again is due to the construction of this component, which is made out of a full metal. So the footprint on the PCB is very limited. These two series are perfectly suitable for high power applications from 0.5 milliohms up to 6 milliohms. As an example of the extremely good power rating of these new devices, I will show you here in this graph the pulse power rating for the 1206 parts of the FM series, which is the FMK. Here shown the 2, the 4 and the 6 milliohm part of the series. At the right side of this graph, you see the continuous operation mode. This is dominated by the thermal conductivity of the device. For the 6 milliohm FMK, we have a continuous operation at 1 watt. For the 4 milliohm part, we have a continuous operation at 1.5 watt. And for the 2 milliohm part, we have a continuous operation for 2 watt. On the left side of this graph, you see the maximum rating for short pulses, and as for the 4 milliohm, you see that we are close to a pulse energy of more than 200 millijoules, which is extremely high for such a small component. This regime is dominated by the heat capacity of the device, and as this is formed out of full metal, we have an extremely high heat capacity and thus a so good performance for the pulses. I should mention that these curves are valid for joint temperatures of 110 degrees C. So if you have lower joint temperatures, the power rating can be even higher. The final example I want to give you is a product called BAN. This is a busbar type shunt, which is intended for automotive applications primarily. And this is available down to resistance values of 25 microohms and is intended for continuous current load up to 1200 amps. These are conditions which occur during situations of extremely fast acceleration in new car designs. This shunt is available in different mechanical configurations, and it is also available in a TCR optimized version. There we use the methods I have explained earlier in this talk. So let me finalize here. I have shown you in this webinar that shunt resistors are excellent sensors for current. They have an excellent long-term stability and they show very small TCR. You can use them even to make a redundant measurement. They are very robust and new designs have an improved power density. I would thank you very much for your attention and I'm glad to answer your questions. Thank you very much.
Thank you so much for that great presentation. And now let's get to the Q&A. We do have some questions that have come in from the attendees, so we're going to move into answering those right now. If we don't get to your question, don't worry, we will have an answer for you following the webinar. And if you haven't submitted your questions yet, you can still do so now by adding that to the Q&A box and clicking submit. Even if you have a comment, we would love to hear from you. Okay, now for our first question from the audience. Do you have reliability for shunt data available? Jan?
Yes, sure. We do have, for every shunt or for every family of devices, we do extensive testing, and due to acceleration models, we do have a lot of reliability data available, which can be sent over by request of the customer. And in addition, we also have a lot of field experience. So every year we are updating our reliability data by the years we have the parts in the field. So every year our database of reliability data is increasing and we get better and more reliable data. So just send us an inquiry and we can send over this reliability data.
Excellent, thank you for that. Okay, moving along to our next question from the audience. Why do you choose full metal shunts for SMD applications?
Well, there are different technologies available for shunts, and each technology is preferable for a given range of resistance values. So for example, foil technology is good for shunts in the range of 10 milliohms and up, and welded parts are very good for 1 milliohm parts and below. But in between there's a range where full metal shunts are really beneficial. So we cover the range of 0.5 milliohms up to 5 milliohms with full metal shunts. And in addition, these full metal shunts are very reliable because there's no organic material included in the design. And finally, these are very good for the pulse rating, as the metal of this shunt has a very high heat capacity.
Excellent, thank you for that. And to the audience, we are in the Q&A session now. You can still send us your question by typing that in the Q&A box and clicking submit. Okay, now for our next question from the audience. Are there any concerns with mechanical stress in the shunt when the mounting surfaces are not flush with each other?
So far we have no experience with mechanical stress in the shunt, as long as it is a proper process in the application. So for SMD shunts, the welding process and also the material of the PCB board is important, but this is rather standard in the industry. And as for busbar shunt configurations, there's also no concern or even any incident considering the stress inside the shunt.
Excellent, thank you for that. Okay, and let's see what's next. Wow, a lot of great questions in the queue here. To the audience, please keep them coming. We would love to hear from you. Okay, here's our next question. Are there design considerations regarding short-term power pulses?
As I mentioned in the talk, and this is a maybe quite complicated pulse power diagram, for short-term power pulses, the heat capacity of the shunt is the important. So for any given device from us, you can use this diagram to calculate or to read out the correct value which can be applied as a power pulse for this shunt. And in the qualification of a device, we also do extensive testing so that it's not only secured by mathematical calculations, but also intensively tested during the qualification of the shunt.
Excellent. Thank you for that. And thank you to the audience member that sent that in. Thank you to all the audience members that sent in questions so far. And as we are in the Q&A session now. You can send us your question. You can type that in the Q&A box and click submit. And as mentioned, we're going to try to answer everybody's questions today. However, if we don't get to your question for whatever reason, we will reach out after the webinar is over. Okay, let's see what's next. Okay, great. Here's our next question from the audience. Can you explain more about the power rating of a shunt?
Okay, thank you for that question. So it seems that power is quite an interesting topic. So in the question before, I just mentioned the short-term power pulses. On the other hand, you have the long-term or the continuous power rating. As mentioned, for this, we have the rating for the shunt itself. So, for example, a shunt which has a continuous power rating of 5 watts is designed or intended for a continuous power of 5 watts. What has to be considered that this heat which is generated can also be transferred from the shunt to the environment. So for an SND type of shunt, this means that you have to look in your PCB design that, for example, you use something like thermal vias or PETs or whatever design elements which have to be capable to transfer the rated power from the shunt into some cooling area. And the same is true also for busbar designs. Here you have to ensure that you have a good heat conduction from the device into the busbar. So you have to ensure a good connection between the shunt and the busbar and an overall thermal design. I hope this answers this question.
Thank you for that, as do I. And to the audience member that sent that in, if you have any further questions or comments, please feel free to send them in. Okay, let's see what's next. Okay, great. Here's our next question. Are shunts applicable in designs intended for functional safety?
Okay, thank you for that question. Yes, shunts are available for designs which are intended for functional safety. I have to mention that the shunt itself, as it is a passive component, cannot hold any ASIL rating. However, as a shunt is a very reliable component, you can use it to build a system and to fulfill any rating for functional safety. And on request, we can also provide you with the necessary data to do the fault tree analysis and to do the fit rating calculation you need. All this data is available on request from us.
Excellent. Thank you for that. To the audience, we still have a little bit more time to go, so you can still send in your questions. I see we have a couple in the queue yet to be answered, so we're going to get to those in a moment. But if you do have any last questions or comments, now would be a good time to send them in to us. Okay, and now here is our next question. How does the resistance material contribute to the overall performance of the shunt?
Okay, that's also an interesting question. So, as I had shown in the talk, one important property of the resistance material is the TCR, and obviously this is a big contribution to the overall performance. However, as you can vary the specific resistivity, you can also have an influence to the overall material used in the design. So if you use a material with a higher specific resistance, then you have less material applied, or if you use a lower resistive material, you need to use more material to get the same resistance value of the shunt, and thus you can influence the size of the device, but also the heat capacity of the device. So by playing around with the resistivity of the material, you can also optimize size and short-term pulse properties of the shunt.
Excellent. Thank you for that. Okay, let's see what's left. Okay, great. We have 2 more to go here. So here's our next question. What contributes to the temperature coefficient of a battery management shunt?
Yeah, basically there are 2 contributions. On the one hand side, it's the material property, and on the other hand, it's the design. I had some examples in my presentation where I showed that the overall temperature coefficient of a battery management shunt is always a combination of the property of 2 materials, the resistance material on the one hand side and the copper on the other side. And by using a good design, you can combine these 2 properties in a way that you can fine-tune the temperature coefficient to 0 or even to a negative value just by the design of the shunt.
Excellent. Thank you for that. And to the audience, looks like we have 1 more question in the queue for now. So if you do have any last questions or comments, now is definitely your last opportunity to send them in. So please, if there's anything else, please send them in and we'll try to get to it. But for now, this is our last question for today. And here it is. Why is temperature compensation at shunt level so important if it can be calculated in the microcontroller?
Okay, this is also an interesting question. So if you do temperature measurement at the shunt level, so for example, if you use NTCs and calculate the temperature at the shunt level, and you know the TCR or the full TCR curve of the shunt, in fact, you can calculate the TCR by the microcontroller and compensate for the TCR. However, with such a temperature measurement, there's always an error associated, and there's also a time delay associated. So when you use temperature sensors like NTCs or any other temperature sensor, you typically have a delay of some seconds, and you also have an error, and all this contributes to the overall accuracy of the measurement. And when you do the compensation at the physical level, at the shunt level, then your TCR curve becomes very flat or even close to 0. So all the measurement errors and also the time delay errors you have in your calculation become negligible small, and the robustness of the system is much higher.
That's great. Thank you for that. And we did receive another question. So here it is. Can you explain the 2D barcode in more detail?
Yes, sure. So we do have the option to measure all the relevant properties of a shunt at final test in our factory. And what we can do is placing these values individually for each shunt into a 2D barcode. So if you do the initial error of the shunt at room temperature and the initial deviation at an elevated temperature, you can put either these two values onto the shunt, or if you're using a mathematical formula to compensate for that, you can even put the coefficients of that formula into that shunt. So you have individually for each produced one the exact initial error and also the temperature behavior associated with this shunt. So if you're using this shunt then and putting it into an application, you can read out these values during manufacturing of the device and use this in the calculation of, for example, the battery management system or the motor controller or wherever you're using the shunt to compensate very precisely for all temperature and also for all initial errors without the need to calibrate in system.
Excellent. Thank you for that. And that was our last question. So we are going to wrap things up right there. So again, thank you so much for that great presentation and also taking the time to answer some questions from our audience. And of course, we'd like to thank our audience for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you can come back and watch it again or share it with your colleagues. And lastly, please take a moment to complete a survey, which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.